Hello, everybody, and welcome to the Spring 2026 RE for Ukraine project showcase. We run these events twice a year, and it's really wonderful to see so many. I am on the faculty at New York University, where I teach computer science and data science, and I also direct the Center for Responsible AI at NYU. Uh, the goal of the center is to make sure that we're using AI in a way that helps all of us, not just a select few. And in the case of this program here, the goal is to make sure that we are able to think about the responsible use of AI internationally, globally, and in particular, to make sure that amazing Ukrainian talent is plugged into the global AI ecosystem of research, development, and use. So I'll just give a very quick overview of the program. The goals of RE for Ukraine are to provide a sense of normalcy and high-quality research opportunities to Ukrainian students, to create impactful and rewarding mentorship opportunities for graduate students and postdocs, primarily in the US and Western Europe, and build research capacity in Ukraine in STEM and specifically in AI and responsible AI. As you all know, the structure of the program is such that we start in the fall, we do an open house, and then we match students with projects. These are really exciting projects from mentors from all around, I mean, not quite all around the world, but from many, many countries. And in the fall, these teams work on their projects for academic credit, and then in the spring, those of you who are enjoying your projects and are making good progress are also continuing to work with us and are receiving a stipend. And so now is the showcase, which is really, I guess, the main showcase of the year that presents some results of work that you all have been doing for 2 semesters at this point. And then some of you may continue to work with us over the summer. We will have more details about that after the showcase. Just again, a little bit of an overview here. So far, the program started in June 22, and so far we have been fortunate to work with over 100 students from 18 Ukrainian universities who have collaborated with 70 mentors from 35 academic institutions across 12 countries. And we have so far published 19 papers. As a result of this work, I encourage all of you, students and mentors, to be sure to let us know when you publish a paper. We would love to know when there is a paper on archive even, right? Even if it's not been yet peer-reviewed, so that we can celebrate with you and can help you amplify some of these results through our communication. I'd like to hand over to Yaroslav for just a couple of minutes to give us a reflection.
Yeah. Hello, everyone. Greetings from Lviv, from Ukraine. First of all, I would like to thank Yulia. Yulia just told for a few minutes about this really big project. Indeed, it's 4 years of continuous efforts and continuous help, continuous fundraising, and continuous work with students and with mentors. So, Yulia, thank you very much. You, your school, New York University, for all these efforts. What I think changed from the 2022 to now is the role of responsible AI. At least for me, in 2022, I thought this is a good part of our programs to have. Now this is essential part. Now this is, we can't now understand the world without responsible AI and without being ethical, transparent, human-centered in this growing growing speed of AI tools. So I think that the work we do all together is really important, and its importance grows. Thank you very much. I would like to thank all contributors, all mentors, all students, all organizers for your work, and I'm excited to see the results of your work. Thank you very much.
Thank you, Yaroslav. Next, a couple of words from Tanya, and then Anya will speak, and then we should all take a photo while we all are here. So please don't, Yaroslav, stay with us. Yeah, thank you.
Yeah. So I definitely joined these great words from Yaroslav, and thank you, Julia, for the fourth year together. Thanks, Anya, for organizing all together. And of course, my huge thanks to all the mentors who support our students in Ukraine. And you did like tremendous work. So I congratulate all together with another great year, great projects, strong publications, and even bachelor thesis. So I'm so happy that Responsible AI is now just not something new in Ukraine, but it's became with each year with this program stronger and stronger. Thank you to you, Julia.
I'm still smiling about hearts from Yaroslav. Hello, everyone. Congratulations on reaching the end of the semester, almost reaching the end of the semester. Project reports are due next week, next Friday. So things are trickling in, and I see there are some publications happening. So we're very excited. Please let us know. We celebrate them. We keep track of them. Special thank you to our mentors. This would not be possible without you. And yeah, let's maybe get to it.
Yeah, let's all, or those of you who can, turn on your video so that we can take a quick photo of all of us. I'm actually going to stop sharing slides for just a moment. And gallery, I want gallery view. We have 27 people here. Might need to do, oh, we don't all fit on one page, sadly. Sorry, just a moment. Let me try to center this for a second. All right, so smile, everybody. 1, 2, 3. Another one, just in case. And let me go to page 2. Just a moment. 1, 2, 3. Thank you. All right, I'm going to share my screen again. So the way that we are going to do this is the same as we did last time. In the fall, we will go through the projects in sequence. You all know when you're next, but we can also put into chat which team is next. Each team has 7 minutes to speak, and then there's going to be maybe 1 or 2 minutes for questions and answers. So let's go to the first team, LLM form.
Hi everyone, my name is Marco. The project I've been a part of is LLM for ORM, exploring LLM as energy efficient alternatives to ORM frameworks. And I'd like to showcase what we've accomplished during the second semester. Next slide, please. Before that, let's have a brief recap of our first semester. We focused primarily on building an ORM-based SQL rewriting pipeline, attempting to optimize ORM-generated TPCC queries in terms of energy efficiency, and measuring the consumption. Next slide, please. This semester, we decided to broaden our scope, stepping away from the strict ORM focus to explore LLM-assisted SQL optimization as a whole. Crucially, we also prioritize the semantic equivalence of the queries to ensure that the intent is preserved post-optimization. Next slide, please. The baseline approach prevalent in the current literature and the one we initially adopted is very straightforward, a direct SQL to SQL rewrite. It feeds the original query to the model, which attempts to translate it directly into a more efficient form. Next slide, please. Our proposed approach, which hasn't been explored in state of the art yet, looks like this. It's a two-stage pipeline. First, the LLM translates the SQL query into a natural language intermediate representation, and then it turns it back into optimized SQL. This approach aims to preserve semantic intent while stripping away inefficient architecture. Next slide, please. We identified two significant limitations during this semester. First is the data scarcity. we found that there is an absence of dedicated data sets for evaluating SQL optimization. The data sets we tried, such as TPCC, TPCH, and AuctionMark, were found unsuitable for our project as they were designed for a different goal, to measure the performance of the database itself rather than an optimizer's capabilities. Next slide, please. The second limitation is tooling. Even the most sophisticated state-of-the-art semantic equivalence checkers are designed to work with a small subset of SQL. Therefore, our experimentation demonstrated that integrating such tools, namely QED, presented significant challenges for our pipeline. Looking ahead, we plan to compile existing data from various sources such as textbooks, articles, into a standalone dataset for SQL optimization. This will allow us to benchmark our approach against existing rule-based optimizers. And finally, we will assess the energy consumption of the rewrite and determine the so-called break-even point, demonstrating whether the saved energy outweighs the inference costs. And ultimately, we aim to contribute both a dataset and a paper, targeting the EDBT-ACDT 2027 Joint Conference in Lille. That's it from us. If you have any questions, I'd love to hear them.
Thank you very much. Very nice work. What was your favorite part of this work, and what did you find most difficult?
Definitely my favorite part was the fascinating team I was working with. They gave me a lot of guidance, a lot of insight. And the most frustrating part, the most hard one was contacting other researchers that have published some papers without providing code artifacts, which was crucial for our research, and that kind of gave us a bunch of roadblocks, but we managed to overcome it.
Yeah, I mean, I agree with you. This is really very difficult. Reproducing results, right? If code is not published, if data is unavailable. So let's all take this as a lesson, I guess, right? We should be doing responsible research, not just responsible AI. So, are there any other questions for Marco? If not, let's go to the next presentation. Thank you, Marco. CAUSAL-SHAP is next.
Yes, hey everyone. So my name is Maxim, and together with Josh Loftus and Sakina Hansen, we have been working on the topic of causal Shapley values. Next slide, please. One of the central challenges in machine learning is not only about the building accurate models, but also explaining their predictions. And Shapley values is probably one of the most widely used explainable AI approach. When we use SHAP to explain a model prediction, we usually want more than just a list of feature contributions. We want a causal story, which will explain which features actually drives the output. Standard SHAP cannot answer that because it captures correlation and not correlation. Many causal extensions of Shapley values go further, but they often give only the total indirect or total direct effect. Some path-phase approaches try to break the single indirect effect apart, but existing approaches have some problems. So one of the key approach discussed in the literature is the pathwise Shapley values. It can return like their attribution in a certain causal structures, as we'll show later. And for example, another approach like Shapley flow, which gives edge level credits rather than per path scores, which doesn't allow us to actually doesn't answer the question how we actually construct the pathwise contribution from that. And also one of the main, on top of that, neither connect to the classical mediation quantities, like natural direct effect or some other effects that are widely used in epidemiology or fail ML studies. And that's a gap we aim to fix. Our method is portion limited Shapley values. That's exactly what fills the gap. And the idea behind it is simple. Instead of asking what changes when we condition on the mediators, we ask how much of the treatment effect disappears when we pin the mediator to a fixed value. This quantity has a long history of mediation analysis and is actually called a portion limited effect, which is basically where our Shapley values approach took a name from. And using this effect, we can actually run the standard Shapley game, or it's a group of mediators, And that's actually what gives us a clean mediator decomposition, even when features interact. Because this Shapley game, Shapley steps splits the interaction term fairly between them, so the score still add up to the total. These three properties come for free, so these three properties of Shapley values. Um, at the sample level, the peer mediator score sums to the total mediated effect. At the population level, it sums to natural indirect effect. And under additive separability, our PE-sharp approach actually recovers the portion pathwise Shapley, path specific effect, the one which was initially introduced by the Pearl. Um, and these are the alignments that neither of the approach produce now. Next slide, please. And the two practical questions is, can we identify this from data? And how can we actually compute it? Identification is straightforward when there is no hidden confounders, where there is no backdoor path from the treatment to outcome, and there is mediator group contains its own ancestors. Then we can just compute this directly from the data, from the observational data. In case where it doesn't hold, we still can use the G formula on the relevant ancestor set. For estimation, if the model is variable, we can use Monte Carlo. In case of restricted access to the model, like it's some expensive API or some large foundation model that takes a long time to run, we can use doubly robust estimation. Sorry. Next slide, please. To later our approach, we built three synthetic examples, S1, S2, and S3, which is basically the simple chain, parallel chain, and the combined one with both nonlinearities and the confounding. On the chain, PV-sharp gives essentially zero attribution to the upstream mediators because condition on the downstream ones cuts its influences, and PE-sharp recovers the full effect. So you can see on the column S1 we have almost zero for the PV-sharp. Which can actually hide the effect of the mediators. And also note that for PE-sharp and it's identically almost the same as the natural indirect effect. So on a population level, it basically sums up to the natural indirect effect. So this way, another example is a parallel benchmark. Pathwise sharp actually gives the opposite sign from the analytical answer, and in our case, analytical answer is again natural indirect effect. So reading pathwise sharp contribution would lead to the wrong conclusion about the pathwise actually helps if we consider the classical causal background. Next slide, please. Another example, we applied P-sharp is a compass data set, which basically one of the central to debate about racial bias. We model race as a treatment, age as a confounder, and there's three mediators. Here, our property one is not satisfied, so we use the G formula for estimation. And both of the approaches agree that most of the effect comes from the first mediator, but the key difference here is still preserved, as the P-sharp gives a clean per mediator decomposition and sums up to the effect compute on the whole mediator set, and PV-sharp doesn't give any decomposition guarantees. And second, PV and P-sharp disagree in the sign for both of those examples, which actually aligns with the example we had previously on static data. Next slide, please. Our main limitation is that PE-sharp is currently channels only binary treatment and requires causal DAG, which motivates our future work. And to summarize, PE-sharp is a natural choice when you want to disentangle pair mediator contribution in classical mediation terms, which can be used for fairness auditing, epidemiology, and any other policy analysis. We'll be happy to answer any questions.
Thank you very much. Very interesting work. Does anyone have questions? I have some, but maybe some other. No? Okay. So this is very interesting to me, and of course, we also in my group work quite a bit on structure and how it informs Shapley value computation. And so I want to ask about the kinds of tasks that you are working with, right? So here you have classification as well as risk assessment. Were there any differences in the way that that your mechanism was set up for these kinds of outcomes? Or is it kind of seamless to replace classification with risk assessment?
It's mostly seamless.
The target variable is different, right? So does that impact anything?
Yeah, so like overall, the difference is mostly seamless. So the answer will be just the quantity we're getting will just be different. So in case of classification, we can get some residual differences. In case of regression or any other similar models, we'll get just a difference in terms of the target quantity. But the overall, the matter is set in the same way.
What are you most excited to work on next in this project? I know you listed some future work, and everybody says, you need the causal graph, but you need the causal graph. So
Yeah,
what else? Yeah.
We actually that's what actually I think that's one of the most exciting promising direction overall, not only for the specific direction of pathway explanations, is somehow find a way to compute the Shapley values when we do not actually know the causal graph for sure. We might get some different estimates. So we actually been working this a bit, and I think that's the direction I would want to continue the most. I love this causal back uncertainty.
Well, let's talk because I know of some work also that attempts this. Okay, great. Thanks very much. The next team is KG-LLN. Please go ahead.
Hello, everyone. My name is Metro, and together with Sviatoslav, Severin, and our mentors, Ernesto and Artur, we are working on aligning knowledge graph alignment with using large language models. Next slide, please. So basically, what are knowledge graphs? They are structured representations of entities and relationship between them. The alignment is the process of finding equivalent or related concepts across different ontologies or knowledge graphs, and matching, global matching is a matching approaches that optimizes mapping across the entire ontology rather than comparing entities independently. So, and basically, the problem is that knowledge graph alignment is difficult because different ontologies describe the same real world concepts using different terms, structures, and different levels of details. Therefore, large language models can help automate this process by understanding semantic meaning behind labels and relationships. Next slide, please. So our primary tool for doing the alignment is ontology alignment system named LogMap. Our contribution is in this Oracle module, which consists of the LLM, which does the validation step. Next slide. So main prompts and data sets that we use for this research are prompts which contain different combination of extended context, synonyms, or natural language friendly formulation. And the data sets are mostly biomedical from the Ontology Alignment Evaluation Initiative track, are anatomy, bioML, and large bio. Next slide, please. So our first important point in the research during this semester are mediating ontologies. So LogMap Bio is an extension of the LogMap system introduced in the previous slide. It uses a mediating ontology approach by leveraging large external biomedical ontology to identify indirect correspondences between concepts from two different ontologies. And instead of matching entities only by direct lexical similarity, it maps both ontology through shared concepts in the mediator, improving alignment accuracy in the complex biomedical domains. Our contribution is on the algorithm on the right side. You can see at the stage 3, when there is a composed mapping produced by ontologies mediating. Can you go on the next slide, please? On the left side, you can see all the mediating ontologies that were used for the anatomy data set. And on the right side, you can see that, in fact, the large language model can improve significantly the results by approximately 0.23 of one score. being new, I think, state-of-the-art approach. Next slide, please. Another point of our research is the repair mechanism, which goes after the previous part. So logmap performs basically logical repair by detecting mappings that introduce inconsistencies or unsatisfiable classes when two ontologies are merged. It then removes the conflicting mappings to preserve the logical coherence of the final mapping. By usual heuristics of the logmap, basically the plans that have the highest conflict score are removed. In our case, we look at the semantic information which contains within these plans and let the model decide which mapping should be removed. Next slide. We can see that LLM performs slightly better on complex data sets, and the data subsets that have high false negatives values are pretty challenging for both approaches. Next slide, please. Another point of our research was the few-shot RAC. So in the previous term, we were exploring few-shot experiments. In this time, we would try to using some similarity approaches. Retrieval augmentation substantially increases the recall, as you can see on the table on the right. However, it reduces the precision. So this suggests that the dynamically retrieved examples introduce variability that biases the prediction toward positive classification. And retrieval augmentation therefore favors coverage over discriminative precision. Overall, fixed few-shot prompting provides the most balanced performance in terms of precision and recall. Next slide, please.
In terms of experiments for the LLM models, we mostly focused the term to relate the open weight models and the pay models compare their performance. The important part that we saw that previously the best result was with Gemini 2.5 Pro. It was close to 0.77. And the other models previously had a result like close to 0.5 and then to close to something like 0.7. And for that term, we can see that after we evaluated a few more models recent and tested different like prompting techniques or some other parameterizations, the gap is getting closer and closer. So now the gap is close to 0.02. And another important part that we can see here on the bottom plot that actually we can even improve the performance if you try to combine the best models for each dataset or the dataset type. And theoretically, it can show the combination of a few best open weight models can overcome the Gemini 2.5 Pro model. Some of those experiments will be partially matched lately. Can we move to the next slide, please? Yes, another analysis important part here was the price versus performance. How cheap we can get the experiments, because previously the experiments were pretty pricey and we were limited with the number of samples or experiments. And here we can see the Pareto plot for all the models and experiments that we tested. We could clearly see that we are close to the plateau here, and with the new models released, those plateau is getting like cheaper and cheaper. So now we can experiment with like 10, 100 cheaper models and do it fastly and test different things. On the next slide, please. Some important notes about the price. First of all, most of the price comes actually from the reasoning tokens, but those reasoning tokens actually like provide the better performance. So another steps that we were trying to do to minimize the reasoning by getting the best performance. Another part is error rates. Actually, LLM models are pretty stable. Only like if you up to 10 models that we tested showed error rates close to 0.5, close to 5%. And most of them they are successfully retried. We can see it on the left bottom plot. And in terms of person time, we can see that actually all the models that show the best performance results, they have solid person time. So there are no models that we need to wait like a few minutes to get the results. So it's also getting better in terms of experiments. And if you can move to the next slide, please.
Yes, so we also tried to combine the LLM outputs So we used some like default approaches, but well, like theoretical ensemble could be like very large, but it's largely due to the randomness in some difficult cases. We didn't quite get a lot of improvement from this. So next slide, please. So we tried another approach where we would combine for this one LLM model, but using different prompts. And this is far more promising approach. I can see that it helps almost on every Gemini model. And next slide, please. Also, part which we explored were about confidence. So we asked LLM about how confident it was in that mapping, and almost all LLMs provide like a good, better F1 score with bigger confidence. Though their distribution of their confidence scores is quite different for each LLM, and depending on whether it's light or like pro model. Next slide, please. So it motivated our approach whether we can save cost and be more cost effective. And we tried using the bigger model as a smaller model on all the prompts and re-evaluate this bigger only the ones where it were unconfident. And we saw that this approach can actually save some costs. And next slide, please. And some other insights that basically the zero temperature where is the best for the classification, and some maybe you saw like the double prompt approach from the Google. It also works on our task, giving a slight performance boost. Next slide, please.
So in terms of our achievements for that part, we were happy to the main track of ESL 2026, the conference that took place at the end of March. Also, we got the second place on the ontology alignment relation campaign. The second place with our log map LM system using Gemini models, and if it can move to the future work and plans. So yeah, in terms of future work, so we are eager to explore more data sets for the mediated ontology testing. Also, we want to extend the knowledge base for fish shots, Hierarchical, and some other different techniques. We wanna find the trade-off between reasoning and fish shots because fish shots are mostly much cheaper than reasoning tokens, and they can show the same result. Yes, also we want to find the optimal cost for the silicon and performance, and test fish shots on the new most promising models as they are most cost effective. And our like main goal and plan is to target the journal paper. We are like working on yeah, that's all. We are happy to answer your questions.
Thank you very much. This was a little bit longer than we wanted, right? But of course, you are a 3-person team, so that's okay. But for people who are 1 or 2-person teams, please stick to the 7 minutes. Thank you very much. Really nice work. I have a burning question. I'm sorry. What is Jordan's index that appears in all of these plots that you showed? I wasn't sure whether higher is better or lower is better. What is it?
Yeah, higher is better. Jordan index is actually like sensitivity plus specificity -1. So it's better for the errors analysis than the simple F1 score.
So lower is better once again, right?
No, higher is better.
Higher is better. Okay. All right. Do others have questions? Maybe one question? Okay, let's move to the next team in the interest of time. Please go ahead.
Next slide, please. So our project is UHAT-RE, rule extracted explanations from hard attention transformers. Next slide. So the problem here for us was to extract the rules that explain the behavior of the transformer. As we all know, the problem of black box continuous math. So our objection here was to define and implement simplified transformer model, describe the rule extraction algorithm. Then we generated a set of LTL formulas for training on the data set, and then evaluate the results of our extracted rules, how they actually match the real behavior of the model. Next slide, please. To understand what the simplified transformer does, its only job is to look at the input sequence of symbols and classify it as positive or negative, answering the question, does this sequence represent a valid word existing in the formal language specifically? Next slide, please. And to understand what these rules actually are, we want to extract them as linear temporal logic formulas. And LTL is a mathematical language that lets us verify states over time, for example, saying that event A must not occur before event B. And because our model is leftmost hard max attention, the token choices are strictly discrete. And it lets us track the semantic history, actually tracking when token P1, for example, looks at token P2. And this lets us build the bridge to translate continuous matrix multiplication to the actual linear temporal logic formulas. But extracting these rules, next slide, please. Extracting these rules layer by layer presented a computational bottleneck because on each layer we assume that any symbol could sit next to any other symbol, and for the alphabet size of 33 across 3 layers, it very soon presented the complexity of extracting more than 1.7 trillion rules, which caused the machine to freeze and not be able to compute all of them. So the decision for this was to only isolate the positive sequences, which are classified to pass the threshold. And for them, we apply the unfolding operator, which works recursively backwards from the final layer to the very first layer, presenting the logic for all the winning paths. Next slide, please. Here you can see the final formula part of it. It is much bigger than here on the screenshot from the terminal. But here it represents the complete positive decision-making behavior of the model. Next slide, please.
Okay, and however, in order to evaluate how well our transformer performs and how well we extract the needed rules, we had to create a LTL dataset that is generate formula that satisfy LTL logic, and at the same time, we also wanted to have finite traces that we could use for evaluation. So in our core run, we had alphabet size of 6, and also we had it in 33, but it failed because it was very computationally expensive, and also we purposely wanted to have it balanced. In order not to have it not verified or verified just randomly, we used black reasoner in order to verify it externally, whether it really satisfies our logic. And we successfully did it because we had 1% agreement in the run that we used for the evaluation. Then we used this LTL dataset for hypothesis testing. We wanted to show that hard attention helps us in the settings where our symbolic transitions doesn't have high entropy. Also, we wanted to show that the gap between softmax transformer and our version of transformer depends on the depth of the layer and the dynamics effect. And also, we just wanted to show how similar our reference formula and the formula that we extracted are. For this, we used a bunch of metrics like accuracy, hierarchical, and also we used record similarity for the formulas themselves. So here you can see comparison first between the layers in the simplified hard transformer. In this setup, we used LTL formulas dataset generated, as I already said. And as you see here, when we use 3 layers, it outperformed statistically significant. We used the tests. And yeah, so in our further work, we focus on exactly 3 layers. Okay, then as for a comparison between hard attention transformer and softmax transformer, as you can see on LTO task, hard attention transformer quite surprisingly for it can be, but it outperforms softmax attention transformer. But it is really statistically significant in comparison to other problems that we considered, because in addition to our generated formulas and dataset, we also used real data, such as poker data, and also we had to use balanced parentheses in order to classify it. And only in the case of LTO formulas, that's the difference between softmax and hard attention transformers was significant. And also we checked similarity between the formula that we extracted and the reference formula, and in the level of match between the output, the labels for the sequences that they give, they have almost 50% similarity, but at the same time, they require similarity. So how their tokens are similar to each other, we have almost twice bigger result similarity. In our further work, we want to optimize the alphabet size in order to improve our unfolding procedure, and we can use different methods for it, from graphs to some stochastic methods. And also we want to improve results of the similarity in order to semantic overlap and semantic match be as high as token-Jacquard similarity. Thank you.
Thanks very much. We're a little bit over time, so maybe one question. Michael, I see you unmuted. Do you have a question?
I think I'm not muted. I didn't understand the black checked semantics. So if it's possible to quickly explain that.
Where is that?
It's a few slides in.
Here?
Yeah.
Okay, it's external verifier. It's called black because it's called has abbreviature. Yeah, it's bounded LTL satisfiability checker. So it checks whether the formula satisfy the LTL.
Thank you.
All right. In the interest of time, thank you. Very nice talk. In the interest of time, let's go to the next one, which is synthetic neurosymbolic task generation. Please, Mikhailo.
Yes. So hello, everyone. My name is Mikhailo Beleshny, and today I'll present project Synthetic Neurosymbolic task generation with controlled constraint complexity as continuation of our previous work about hierarchical classification. And this work was done with my 2 wonderful mentors, Michael Bendik and George Zombori. So next slide, please. So first of all, let me explain what is learning in the presence of constraint is. So learning in the presence of constraints is a task where the main where target is objective, but we also have to simultaneously satisfy the constraints. So for example, you can consider a computer vision model where model can say that it sees a sparrow, but it's not a bird, and it can violate our predefined constraints. And we want to avoid this, and that's why that's an interesting task, especially in high-stakes scenarios. So next slide, please. So our previous work about constraint multi-label classification work, our main conclusion was that autoregressive models can better satisfy the constraints. But the main limitation we mentioned in the paper is that we relied mainly on 11 generated dataset, and we had absolutely no control over the settings in such dataset, especially the constraints. So next slide, please. So it is mainly our motivation, because most neurosymbolic datasets are real-world datasets that are generated with domain knowledge. That means that their constraint structure is fixed. That basically limits the controllable analysis of different neurosymbolic approaches in this domain. Next slide, please. Sorry, one back. No, next. Yeah, this one. So that's why we designed NSCC. It's a neurosymbolic synthetic benchmark that generates constraints and the dataset that is consistent with this constraint. So it consists of two stages. So in the first stage, we generate a constraint. Constraint, it's logical formula that limits the output space, and the generator mapping. That is basically an input-output function that defines the main learning objective. In the second stage, we align those two together to generate neurosymbolic learning problem. That is dataset and the constraint that will be used for the training. So next slide, please. So yeah, so let me explain each of these stages in a bit more details. So for the constraints, we support CNF formulas and the formulas in linear real arithmetics. So we can see the two examples, formulas that we support. For the generator mapping, actually, it can be everything that you can provide. It can be your own function. It can be existing dataset. But by default, to allow more control over the generator mapping, we trained a random neural network where we can enforce different functional properties with different losses, like diversity, entropy, or the correlation if, for example, you want to test how your approaches works if it assumes independence, for example. And overall, we combine those two with dataset alignment, and we support two approaches. It's filtering and fixing. In filtering, we just discard the samples that doesn't satisfy the constraints, and in fixing, we just fix those samples to make them satisfy the constraints. So again, all of these parts are fully parameterized, so we can generate constraints with different settings. You can just tweak number of clauses. You can change the form of the constraints. You can make the generator mapping larger, smaller. It depends on your use case, and it really allows more controlled evaluation of neurosymbolic approaches. So next slide, please. So in general, this design opens a huge, I would say, perspective for future work, but here we only want to present one, in my opinion, the most interesting experiment that just shows that our generator is capable of showing many different interesting behaviors. So in this example, we tried to change the constraints, and we decided to change CVR, so that's close to variable ratio. It's a primary metric to measure how restrictive and complex constraint is. So with a more close to variable ratio, we have more clauses that just restrict space more. And on our experiments, we compared three-set constraints and linear real arithmetic constraints. And we show that for three-set constraints, the problem for the base model for simple dense neural network that is constraint unaware is the hardest when constraints are neither too easy nor too hard. So there is a sweet spot where a problem becomes the hardest. It's somewhere in the middle. But for linear real arithmetic constraints in the real domain, we show that when we increase the constraint complexity, when we increase the strictness of the constraints, for our model, it's easier to feed the supervision, but it's harder to satisfy the constraints. And that just shows that fitting the supervision and satisfying the constraint is not always correlated. So that sometimes can be two different problems. Next slide, please. So now we want to present how different approaches can work with our benchmark. So here we compare 4 different approaches. So the first one is base. It's just simple dense neural network. We also tested CCN. So what is CCN? It's just a simple constraint enforcement layer that just attached to the simple neural network and just fixes the constraints on the inference. So that allows end-to-end training. But very important thing to mention is that neurosymbolic, in general, symbolic inference it's interactable. So there is no tractable way to enforce the constraints. Therefore, different approaches has to imply some simplifying restrictions. So CCN fixes each variable step by step, so that can result in some suboptimal fixes, but in general, it just allows the model to be trained together with this layer end to end. Another approach is just base solver, where we just predict the output with a base model, and we just use a solver to find the closest satisfying assignment, just to make it satisfy the constraints. And the basic, it's a approach that we proposed in our previous paper that adds learnable autoregressive model on top of the base model. And in this plot, we report the relative improvement in accuracy over the base, and we also report violation ratio for base and basic, because base CCN and base solvers, they guarantee constraint satisfaction by design. So first of all, the base CCN approach, it actually degrades when we make the constraints more restrictive, because it requires a constraint compilation process. And with the more complex constraints, we see that this constraint enforcement layer can even make the performance worse comparing to the base simple neural network that is absolutely constraint unaware.
Mikhailo, please wrap up. You're at 8 minutes.
Oh, sorry. Yes. And just to motivate, to proving our point from our previous research, our basic model outperformed all other methods we consider in this experiment, and moreover, it produces close to zero violation ratio that kind of proves our previous point from our previous paper that a sequential autoregressive model can improve model's ability to satisfy the constraints. Yes, next slide, please. And yeah, so overall, we created a Neurosymbolic synthetic benchmark generator that is capable of generating both constraints and underlying learning function that together is combined into a neurosymbolic learning problem. We also demonstrated that there is a scalability issue of neurosymbolic methods like CCN and DRL, and we also confirmed results from our previous paper. Yes, thank you.
Okay, thanks very much. Very nice work. Any questions for Mikhailo? So I know you've been working on this project for quite some time, right? What's the most interesting part of this for you?
Yeah, I would say, it's nice, but I think the most interesting part for me is probably, I just enjoy using AI, and I think it should be controlled better. So I would say that neurosymbolic approaches and this learning with the constraints is exactly what AI needs to be truly reliable. And I think, I hope it's correct to say that I believe that neurosymbolic AI is kind of a third way of AI. That's what makes me interested.
Great. Thanks very much. Let's move to the next team.
Hello, everyone.
Detection. Yes, go ahead.
Yeah. So today, me and Yulia will present our project AI-powered species detection in underwater imagery. And my name is Volodymyr Vishnovetsky, and I'm a software engineer at Zaporizhzhia National University. And more specifically, I'm going to talk about using modern vision transformers to automatically detect species in underwater images. Next slide, please. So every year, marine scientists collect vast numbers of underwater images, yet most are still labeled manually. And this process that is slow, costly, and highly sensitive to color shifts, backscatter, and motion blur. And these challenges are particularly significant in these benthic habitats, where the whole biodiversity, it spans multiple taxonomic groups, including canopy-forming kelps such as Eclonia radiata, other macroalgae, sponges, sponges, and different diverse benthic organisms. So recent studies suggest that self-supervised vision transformers, such as DynaV3, provide a more robust and data-efficient alternative to traditional CNNs. And this research therefore, question is, can DynaV3 learn transferable representations across multiple taxonomic groups, including kelps, sponges, and other benthic organisms? Next slide, please. So our workflow builds on the framework proposed by Ginzel and the findings from our previous experiments. And last year, we found out that fully fine-tuned DynaV3 outperformed Inception V3, while also, highlighting challenges such as overfitting and data sensitivity. First, we collect large-scale annotation dataset from Squidle Plus platform, then analyze data composition, test different configurations, and generally evaluate performance. And from this curated data, we generate crop images and annotations before training the machine learning model. Next slide, please. And we observed that best performance was achieved when we partially unfreeze the model, and specifically the last two layers of the backbone. Previously, we tested two extremes, we may say, either fully retraining the model or using standard transfer learning with a frozen backbone. However, this intermediate approach provides a better balance in training and requires less computational resources on computing gradients. Next slide. And it leads to more stable training dynamics and improves generalization compared to the other setups. And based on these results, we adopt this configuration as our main model for predicting multiple classes, not just a single species as it was before. And at the same time, we currently limit the dataset to 1,000 images per class. And this is mainly due to strong class imbalance in the data. And to address, we applied downsampling strategy, which allows us to train faster while still maintaining solid performance. Next slide, please. And I will give the word to Julia.
Excuse me for the delay. To sum up what we did the last semester, we benchmark 3 generations of segment anything models on around 5,000 annotated objects from Tasmania that we took from Squidle Plus platform. And our takeaway was that SAM2 gives the best accuracy to speed ratio at around 0.76 IOU. And we moved with this model to our next challenge, namely video tracking. Next slide, please. This is where things actually get more complicated as new challenges arise, such as motion blur, low contrast, and changing lighting conditions. This is particularly relevant to our application case, tracking underwater infrastructure, as for now, without segmentation models, this task is very time and resource consuming. We mainly focus on CPU performance to simulate the capabilities of underwater robots, but we also, during this semester, took GPU performance in consideration as well. Next slide, please. The first tool we tested was BoxMod, a lightweight yellow-based tracker. It was a good baseline for us. It is fast and requires no manual prompting, which is honestly a big advantage. However, it only tracks bounding boxes, so no segmentation masks, and it struggles with the visual ambiguity of underwater images. And on CPU, however, and also on GPU, it gave relatively quick results per minute of the material. Next slide, please. Next, we tried two tools with the SAM2 model. First was Segment Track Anything, which uses, once again, SAM2 to produce segmentation masks rather than just bounding boxes. Here, the interface is way more flexible. We can refine masks with the point, boxes, or existing masks. And the downside of this approach and this tool is the speed. It takes around 90 minutes per minute of the material on CPU and 20 minutes on GPU. Also, every time we need to refine the masks, as you can see, we needed to do that a lot as the masks turn out pretty patchy. We need to rerun the whole process and this 90 more minutes all over again. Next slide, please. And finally, our favorite is ex-SAFE-HIC labeling that combines hero detector with some encoders in a single annotation interface. It is the most intuitive of three and actually supports a very wide range of models. The main issue is here the speed, which takes relatively even longer than the previous tool, and the version mismatches between the bundled SUM2 and the expected API in the tool, which we actually spend most of the time debugging and fixing during this semester. However, despite the challenges, segment and track anything and ex-SAFE-HIC labeling is currently our primary annotation tools, and we will actively use them to build a data set of underwater infrastructure that could be used open source. Next slide, please. At the same time, we will use these two tools, apart from creating the data set, we will test another model that combines capabilities of some models, DynaV3 and the language models, in order to achieve better accuracy and better classification, if I could say so. And here I'd give the word to my colleague.
Yeah, sure. We are planning to also utilize two approaches to test them. The first approach is a bottom-up hierarchical classification strategy. If the model produces low confidence at the leaf node, prediction progressively move up to the up the taxonomy tree with the reliable confidence threshold is reached. And the second approach we plan to evaluate is a top-down classification strategy with localization. In this setup, the model predicts only within relevant local taxonomy branches, and rather than the whole entire hierarchy. For example, the model may first identify biota and then refine the prediction to macroalgae, and within smaller, we may say, context-specific taxonomy subtree. Yeah, and I guess that's all.
Oops. We don't have a Q&A slide, sorry. It seems like, thank you very much. Very nice talk. Any questions? I'm sure people have questions about underwater images and robots. Don't be shy. Anyone? What do you like the most about this work, right?
Specifically, I really like this kind of research opportunity that I'm able to search for different papers and read them and discuss them with our research colleagues in University of Tasmania and also with our team lead, Leo. And by providing this kind of feedback, I'm utterly convinced that I'm able to get some kind of deeper intuition in the research work generally, and it helps me to advance in my career goals, I guess.
Great.
Also, I'll add just a bit. Even though the approaches I'm trying are already set and tested over and over again, in the field of underwater segmentation, we're doing something a bit of a novelty. And I guess that sparks the interest the most. And also, I'm very sorry that my camera is off, it's broken.
All right. Thanks very much again. Let's move to the next team.
Hello,
AI
everyone.
Yes, go ahead.
Hello, everyone. Our project is dedicated to researching propaganda in the context of Russia-Ukrainian war on social media, especially in Telegram. Please, next slide. Russia's information war on Telegram presents a real puzzle. State media and independent war bloggers seems to usually contradict each other. One sanitizes, the other rages, yet both sustain the same war. Our argument is that these contradictions dissolve when you analyze the ecosystem across three layers simultaneously: what they talk about, how they pursue, and what emotions they mobilize. We call the result managed emotional pluralism, a system that tolerates and actually depends on emotional diversity because that diversity never questions the war itself. So next slide, please. For the corpora, we collected Telegram posts from 60 the most popular war blogger channels over 4 years. We isolated war-relevant content only, built our own filtering pipeline, manually labeled a sample of posts, and trained a classification model on it that even outperforms GPT-5 on this task. The next slide, please. To label this content, we built a human-in-the-loop pipeline producing structure annotation across 3 dimensions: emotions, propaganda framing techniques, and topics. Later, we'll take through how it works. Next slide, please. Topic modeling reveals 25 clusters across 3 functional layers: tactical frontline content, ideological identity narratives, and political logistical commentary. The division of labor matters. Bloggers handle the operational layer, while ideological framing saturates even ostensibly factual posts. The next slide. And what is interesting is that the topics are event-driven, of course. Military topics follow technology adoption curves, slow rise, stable plateau, while, for example, diplomatic topics spike and collapse in direct response to political events. That show us that the overall ecosystem is very reactive. Next slide, please.
Okay, so moving on from topic modeling to analyze how propaganda operates in this content, we needed some structured labels. So based on a literature review, we built 2 taxonomies. One is 17 propaganda framing techniques, and the other with 12 emotion categories. You can see some of them on the slide. And then a subset of posts was, a subset of posts was then annotated manually using these taxonomies with justifications, which then will become the ground truth that will let us evaluate how well AI replicates like the expert annotation. Next slide, please. So for the evaluation, we built a 4-stage pipeline. It first pulls 3 similar already annotated posts from vector database and hands them to the LLM as examples. Then the generator LLM produces a structured output. Then there is a discriminator that scores the quality of the output. And if it's not good enough, it goes back to the previous tab. The generator retries with specific feedback. And finally, to evaluate the whole thing, there is a judge LLM, which compares the pipeline's output against the human annotated ground truth labels. Next slide, please.
Yeah, some comment from my side. Since we used not open-sourced large language models, another approach which we tested to improve overall performance is to adding some vectorized data sets with different info, which could potentially fulfill the context of the models to perform better. So specifically, we embedded stop-fake blog posts, which disproved Russian propaganda in scope of war events, and also added some embedding of the description of the events during the whole invasion. Please, Anna, proceed.
Next slide, please. Yes. So across over 1,000 annotated posts, the binary propaganda label really matches human annotation with accuracy of 89.5% of the time, and with an F1 score of 0.92. But the technique detention is much more nuanced, though. So common techniques, for example, like name calling, score above 0.8 with F1 score, while some rarer ones score much lower, simply because there just isn't enough annotated examples to learn from.
Yeah, and the last part, which we've also tried, is next slide, please. Is testing whether the emotion labeling of our dataset would potentially disclose some more features which could potentially be used, but our testing showed that using such subjective features is not useful overall. So to conclude, we did the full research of different approaches about creating the useful training dataset to improve the average performance of state-of-the-art LLMs. And the results were already presented by us. And that's it.
Thank you very much. Very interesting work. Questions? And thank you for staying within the time limit also.
Can I have a question?
Please. Yes, of course.
Did you try some Ukrainian language models pre-trains? Because they were released like half year ago, and maybe you compare them to some proprietary models. Did you do it?
Thank you for the question. Our corpora is overall in Russian with some parts in English, so we didn't even try Ukrainian models for that task.
Okay.
Other questions? Thanks again. Let's move to the next team. Physics-informed generative AI.
Yeah, hello everyone. I'm Artur Pelcharsky together with Alexander Kharitonov under the supervision of Andrei Vaslenko work on a project focused on improving generative AI methods for structure-based drug design. Next slide, please. Before introducing our contributions, let's first look at why generative models have become so important in modern drug discovery. Modern medicine often relies on finding molecules that can bind to disease-related proteins and modify their behavior. Traditionally, researchers screen enormous libraries of compounds in the laboratory, which is expensive and time-consuming. And generative AI offers a new approach. Instead of searching existing databases, we can design entirely new ligands directly for a target protein and evaluate them computationally through docking before moving to costly experimental testing. Next slide, please. Although modern diffusion models can generate diverse molecular structures, they mainly learn statistical patterns from training data rather than physical or chemical principles. As a result, generated ligand may contain unrealistic bond geometries, atomic overlaps, or unstable conformations. Since laboratory validation is expensive, we need better ways to guide and evaluate generated molecules before sending them for experimental testing. Next slide, please. To address this limitation, our first contribution is the statistical proxy potential loss, or SPP. The main idea behind SPP is to evaluate how realistic the distances between atoms are by learning distance distributions from experimentally observed ligands. To make this usable during training, we transform this distribution into differentiable energy-like functions, where lower values correspond to more physically favorable atom arrangements. You can saw how it looks like on our plots. And during previous slide, please. During diffusion sampling, the model is therefore encouraged to generate structures that minimize its potential and better respect realistic molecular geometry. Next slide. Next slide. Yeah. CP can be applied in two different variants, which we call local and global CP. Local CP evaluates distance between pairs of atoms within the generated ligand itself, helping the model produce stable and physically realistic ligand structures. And global CP, on the other hand, evaluates distances between ligand atoms and protein atoms, encouraging more realistic interactions between the generated molecule and the target binding pocket, and to summarize our another contribution of our work this semester was constructing these potentials for more than 200 atom pair types using approximately 200,000 structures from the crossdock dataset. Next slide, please.
Yeah, so one more addition to our loss function was physics-guided global structure regularization. Also, we called it compactness. That's a custom differentiable loss function that minimizes the squared radius of gyration, acting as a global constraint to prevent fragmented or exploded geometries during the generative process. Unlike the standard geometric pooling, our implementation weights atomic position, but the real atomic mass, which we could see on the picture, ensuring the optimized center of mass reflects physical reality and anchors heavy atoms correctly. Also, it includes anisotropy penalty based on coordinate covariance eigenvalues to discourage unrealistic linear or planar artifacts, forcing the model to learn globular, chemically valid packing densities. Next slide. Hyperparameter selection, we conducted a grid search over our proposed loss weights to balance competing objectives during the diffusion process. As table shows, heavily penalizing geometric properties can cause atoms to collapse and destabilize the structure. Instead of optimizing a single peak, we selected the weights 0, 1, 0, 1, and 0, 3. Conceptually, this was an elegant choice that anchored the microstructure without triggering local clashes. This balance stabilized our performance across 3 key metrics we oriented, which is QED, means drug likeness, SA, which is synthetic stability, and Wiener docking, which evaluates the actual docking, which Arthur was talking about before. Next slide. And based on this optimal configuration we choose, we benchmark the model against our baseline across holdout test set of 89 diverse protein pockets from our dataset, which also other works which use this dataset also use. And these three charts illustrate the per protein performance difference of these 3 metrics. So green bar indicates that our physics-informed model outperforms the baseline. And as we can see, the amount of green demonstrates that our model achieved consistent and significant improvement across all the 3 dimensions. For the Wiener, the integration of the SPP provides a highly accurate energetic gradient, and which push the diffusion process towards a favorable local geometries. And by regularizing the process with mass-weighted compactness, the model actively avoids diffuse and non-physical structures. Next. To conclude, this work successfully computed and integrated the SPP into the diffusion process by deriving a differentiable energy landscape directly from experimental structures and combining it with the compactness regularization. We effectively force the model to run chemically valid packing. And our experiments clearly demonstrate that this approach consistently outperforms baseline models in generating realistic high affinity ligands. And connecting to this, looking ahead, we are focusing on 2 main directions. First, we plan to adapt the global SPP into the active guidance model, which will allow us to dynamically steer the diffusion sampling process towards specific molecular properties. And second, we aim to integrate our compactness and SPP into the other state-of-the-art architectures in this field, evaluating the potential as universal enhancement to structure-based drug design. Thank you, and we are ready to answer your question.
Thank you very much. Very nice talk. I just wanted to note that after your presentations are done, you should still stick around, right? Because you need to hear presentations by other people. We're seeing, quite a lot of people leaving, and the expectation is that everybody stays here for the entire showcase, not only until your talk. Any questions? So I have my usual one. What did you like the most and what's most challenging in this project?
Sure. I'll start, maybe. Maybe we'll continue. For me, the most thing which drive me through the project is that on the level of concept, I believe that machine learning and AI in general should be connected with natural sciences, like physics, biology, and adding physical elements to loss functions as here, or like connecting the sciences, I guess is the future of AI, and that's why it was very interesting to work on this project. And the second thing, I guess, that after each iteration, new ideas appeared, and it seems like this topic is almost infinite.
For sure.
To continue.
Yeah. Thanks.
Yeah.
Maybe I also add that it for me, it was the first project where I combined like generative AI with some biology, and it was very like interesting experience for me.
Yeah, I mean, AI for science is a really big field, right? So this is
Yeah.
it's very nice to see that we have a project of this kind represented. Yeah, thanks very much. Next up, quality estimation of labeled benchmark through logic expressivity.
Hello, everyone. We are glad to represent the project of quality estimation of labeled benchmarks through logic expressivity today, here with my teammate and our mentor. Next slide, please. So logical classification of graph benchmarks remains our research focus. However, we recognize the need for a more robust tool. Our core focuses were advancing from synthetic to real datasets, enabling appropriate customizations, and ensuring fast and reliable execution. Yet the core idea for the algorithm remains the same. Here on the right side of the slide, you can see the simplified example of the main process. We take a graph benchmark, apply a logical query, and use its result to group elements into equivalent classes based on how they behave under that query. Our initial version of the tool answered the question of how to do the classification. So the next logical step was to ask which classifications are most relevant and what implications they carry. To reach those answers, we needed the ability to test hypotheses, vary queries, and explore logical fragments in practice. Next slide, please. So the next steps we are taking in order to achieve our goals. Firstly, we expanded the prototype from first-order logics for tuples of RT2 to first-order logics for tuples of RTK to explore more logical fragments. Then we switched from synthetic examples to real data with SQL, CSV, and TTL support. With TTL being a turtle serialization format used for expressing graph data in the RDF model. You can see the example of the RDF model, which is basically a directed graph composed of triple statements of subject, predicate, and object. All in all, this together helped us move from one relation to multiple relations at a time being considered. Next slide, please. Building on this, we also developed a query converter that turns user-written SQL queries into callable Python functions that implement a range of relational algebra operators, including selection, projection, joins, and set operations. So the main conversion pipeline is the next. Firstly, we take the user-written SQL query as the starting point. Then this query is parsed into a structured syntax tree, which then is converted into an internal relational plan. Then we map each column name and alias from the query to its actual table source, so there is no room for ambiguity about where each column comes from. Lastly, the plan is turned into a Python function that can be executed on the data. Alongside these additions, we started optimization for the FA2 refinement pipeline, where correctness could be checked before and after each change easily, with the goal of extracting principles that might transfer to higher RVT and broader logic fragments. But this quickly exposed some challenges in keeping correctness and speed aligned. Exploration of the optimization strategies became the focus of the next stage of our work. Next slide, please.
Yeah. Let me explain why we decided to do this optimization. So as we mentioned, we want to move from synthetic datasets to the real ones. And the smallest one that we were able to find, the smallest graph-based one on which graph neural networks are trained, is this CiteSeer dataset. It consists of papers and references between them. It has around 5,000 references inside these networks and around 3,000 papers total. So before that, before any optimizations, our algorithm took near 10 minutes to run on the first 1,000 edges of this dataset. And taking into account that the asymptotical complexity of it is close to cube one, it means that to run it on the whole 5,000 edges, it would take at least half the day, which is quite a lot, taking into account that it's one of the smallest datasets. Thus, we did a few optimization tricks, and let me explain them to you. So we found a bottleneck in a key component of our algorithm. It's a partial presence of the query result in refinement blocks. It's used for splitting, for further refining on the already present partition. And previously, we used two intersections to do this, and we found a way to do this in one, making speed up in almost 8 times. Also for better memory, for lower memory consumption, we changed the string values from sets to the ideas, which also sped up a little bit the whole process. And we had an idea to make the sorted set based implementation of this algorithm, because sorted sets have better asymptotical complexity for operations that we need, like insertion, intersection, union, and others. But the way we implemented it occurred to be worse than the default one in Python with unsorted sets. But it can be a future step. Next slide, please. So the optimization results that we have is that on the first 1,000 edges, we were able to speed up the process in almost 8 times. And also, during this, we discovered several tools to help us profile our code to find the bottlenecks, understand what takes up the most time, and will help us further with optimization. Next slide, please. It's all great, but until now, the result of our algorithm was just a couple of blocks, or like a couple of sequences with edges which can have a size of up to like in hundreds or thousands, and just seeing them doesn't provide any insight to you. Thus, we decided to add visualization for explainability. Here is what we did. This one example is our algorithm executed on 200 nodes from the paper, and so each edge is a reference from one paper to another, and the color of edges corresponds to the partition to the block the algorithm refines this edge to. Next slide, please. Thank you.
So in conclusion, we developed a robust, extensible toolkit for logical classification that moves from synthetic limited cases to real data with customizable queries and reliable execution. The next steps we would like to take are, firstly, to consider pre-made query batches. We can add predefined query sets for different logical fragments for direct comparison with FO2 and FOK. Then there's the question of optimization. As the number of relations in hierarchy grows, we will need further tuning and would consider a move to a C-family language that could also improve performance. Then there's cloud computing. Running the pipeline in the cloud would make large-scale experiments easier to share, reproduce, and scale. And lastly, benchmarking and applications. With the flexible toolkit that we have now, we could investigate which logical fragments are needed to express properties in real benchmarks, directly addressing the original question we had of can we assess benchmark quality by determining its logical expressivity. This is all. Thank you for your attention.
Thank you very much. Very nice talk. Any questions? Do you have any publication plans? Have you discussed where you might submit this paper?
We are looking into it as we progress with the next steps. It's important for us to take at least 3 of those, and then we would consider the publications opportunities.
As we mentioned, now we are more like building in tools that should help us to test some hypotheses. So we can like having this tool, then assess the quality of data sets, and then we can look how well models perform on these data sets and compare it to how we predicted it to be with this tool.
Yeah, great.
Okay.
Thanks very much. Let's move to the next team, Responsible Edge Intelligence. Go ahead.
Good morning, everyone. Our project is Responsible Edge Intelligence online machine learning for secure and adaptive on-device AI. Next slide, please. To give you some project context, so I want to shift from server to a client. First one is data privacy. We don't need to transfer any sensitive data to the server. We're not so reliant for the network. We can do pretty rich personalization on specific user data, and we can reduce costs on servers. However, it came with some trade-offs. First one, compute is quite limited on edge devices. As a result, online learning plus adversarial defenses are quite hard to implement. However, we have also a symmetric constraint where we can spend additional compute during training, but not during inference. Next slide, please. For this term, we decided to stop on advanced molecular preparation and put online learning on hold. And basically, molecular preparation can be boiled down to three main techniques: quantization, pruning, and knowledge distillation. However, modern research are mainly focuses around combination of these techniques and how their synergy can provide better results. We decided to take one of the recent methods, QUADS, quantization-aware training with dynamic and static pruning, and try to add knowledge distillation to it. Main question, how to do it properly. Next slide. To give you a simple overview, basically, the idea is to run quantization-aware training together with dynamic pruning, and when we hit a target sparsity rate, switch to static pruning to eliminate double-graded approximation. As a result, we want to get more stable training and higher metrics in the end. Four main stages. First one is a warm-up, when we pre-train weights to prevent molecular collapse caused by regularization. Second one is quantization-aware training with dynamic pruning. After hitting target sparsity of, for example, 90%, we switch to static pruning. And the last stage, we fix our topology and just do fine-tuning on weights we haven't delayed. Next slide, please. We mainly inherited experimental setup from original paper, and we decided to fix a student model as ResNet32 integer 2 with 90% sparsity, the smallest model that was presented in the paper, and take different teachers with different quantization types. For the knowledge distillation, we went with basic logic-based distillation, and three main questions we had: what teacher to use, when to enable knowledge distillation, and does knowledge distillation actually improve adversarial robustness? Next slide, please. Firstly, we tried to take a bunch of teachers and check if their quantization how their quantization actually influence results of knowledge distillation. From different models, ResNet32 integer 4 did best, and we decided to do 5 separate runs as methodology described in original paper, and we actually get statistical gain in 0.82%. After that, we decided to understand when we need to enable knowledge distillation, during the whole training process or only after dynamic pruning. Next slide, please. On this plot, you actually can see the results. The final stage after 100 epoch shows that enabling knowledge distillation during whole training process actually stabilize training a little bit more than other techniques. After dynamic pruning did also quite good results, but it's not quite stable, and quad 3 of the baseline actually drops. Next slide, please. Also, we did a simple adversarial robustness benchmark. We take 5 basic adversarial attacks, and we actually were able to get from 0.5 to 2% increase in metrics under attacks, showing that actual knowledge distillation also not only improves baseline accuracy, but add additional security from adversarial attacks. Next slide. Also wanted to actually benchmark it on a way bigger data set, C4 and as you can see, actually all previous experiments failed, and our first hypothesis was that we're not properly configured our hyperparameters. And for that, we decided to do hyperparameter tuning with Bayesian optimization using Optuna. We did 30 runs that spat out 100 GPU hours on NVIDIA T4, and actually we got results that provided 1.06% gain. with quite not standard temperature and alpha values as provided on papers how actual knowledge distillation should be used. Next slide, please. To conclude, knowledge distillation actually enhances accuracy recovery in extreme compressed models. We can use intermediate teachers to bridge the capacity gap between the models and actually get additional supplementary boost to advertiser robustness. Also, complex datasets needs precise knowledge distillation hyperparameter tuning. The key takeaway, our proposed method plus with knowledge distillation actually provides some synergy and superior model performance. As for the next steps is to better analyze hyperparameter influence on knowledge distillation, validate cross dataset advertiser robustness, and evaluate how sparsity actually affects knowledge distillation and the level. In the long term, we want to identify most optimal coding algorithm for sparse architectures, adapt method for transformer-based models, and explore non-logic knowledge distillation methods. For example, feature or relational-based knowledge distillation. Next slide.
Thank you very much. Nice talk once again. Leo, you have a question, please.
Yeah, hi. Thank you very much for this presentation. I think really interesting the teacher framework that you introduced there. So I was wondering, you talked a lot about the training on the GPUs. So when you now talk about the CIFAR 10 or CIFAR 100 data set with the compressed model, what could actually run now your compressed model? So for example, could Aura Nano run your model at certain frequency, or do you have some real world application that we could kind of get a grip on what that actually means?
Yeah, in original paper they actually used just a basic classification method, and mostly they tried to use basic models. I'm not went strictly to the actual how actually parse the model and get the results. At this point, most of the research I see in this paper, they just use like basic classification tags on ResNet and CIFAR 10. It's basically a simple benchmark tool. However, another problem is then when we switch, for example, architecture, everything can change significantly. For example, like quantization can work for any models, pruning is not. And why I actually like this field, because it's not quite predictable. You're not really getting what you expect at first, because, for example, if we quantize weights extremely for integer 2, it does not guarantee that we will get a better performance on final devices, because basically they not implement integer 2 computations. They only operate integer 8 and not lower. So yeah, it's really interesting topic to continue. However, again, this whole resource is quite ambiguous, and we try to fix the scope as much as possible.
All right, thanks for the explanation.
Great, thanks again. So to conclude, we also asked Victoria to speak, to describe some work that she has been doing with us for a couple of years now, right, Victoria?
Yeah. This is a continuation of the previous year of work, which was called Onion, and this year we continue to the project which is called Garlic, and we can move to the next slide. So
yeah, I just wanted to say that Vika is one of the students who's been with this program for quite some time, and she's now doing a PhD. That is an outcome of this work. So please go ahead.
Yeah, so our motivation to continue our work from the last year is that AR modeling is usually taught for computer science students as purely technical skill, but actually it reflects a lot the social side of how people interact, how different
communities work, because we put real lives into like strict entity relationship models, and that's why we came up with the idea and developed this Garlic project, which is about how to teach inclusive methods to ensure that data models actually reflect stakeholders' need and not only reflect the technical correctness of entity relationship models. Yeah, so originally we developed the onion idea, which is about observing the world which we want to describe into entity relationship model. Then we introduce participants who are asked different various questions about how these interactions are happening, that we integrate those feedbacks from stakeholders into entity relationship models, and after the cycle of like technical implementation and feedback, we end up with this kind of fusion of like real input from participants who are representing people from real world, and feedback from technical experts who can make this entity relationship model work. So the next slide. And so we took the onion and we created around it the approach to teach onion in the class. How we did it? Actually, the idea is simple. We created a workshop based on few core things: scenario card and role card. In this idea, scenario card is about the use case where you want to teach people how to implement onion, and role card is really important thing, which is representing like the participants. We do not have them in the classroom, but we want to represent them somehow. So by combining this, we create this Garlic setup, like a relational inclusive co-design process to make sure that students can understand what are the voices of stakeholders when they design entity relationship models. And we can move to the next slide. So during the second part of this semester, we actually created 4 collections of scenario and role cards, which are accessible by this GitHub repository. It has multiple roles and voices to people to use in the classroom. It has multiple scenarios, and it has the whole instruction on how to use it. So it's super ready to use for anyone who is teaching entity relationship modeling for computer science students, or even for students who are not super technical. And I'll explain how we tested it. So basically, to make sure that our system works well, we validate at the end of the workshop by the very simple idea. Each role card has a voice description. So voice is kind of like an like the need of the specific stakeholder or the desire, etc. And at the end of the workshop, if the student can conclude that for this role card, the voice written down in the role card is heard and can be represented in the entity relationship model, then we successfully completed the process. If we can look back at the voice in the card and say, oh no, we missed something, then we just go back to the previous stages and redo the iteration which was not implemented. And by this moment, we completed few preliminary studies, 2 studies with 5 participants each, and also I have implemented the approach with a Garlic framework with this workshop inside my classroom. So I teach decision support systems at American University Kyiv. Please, next slide. Yeah, so I have actually used this Garlic framework in our class, and students had to build this intuition about entity relationship modeling without previous knowledge of how ER models work. So this is an example how we did it online. We had different cards. We had the digital
board where students could write down their ideas and write some observations. By this stage, for example, they didn't have yet information about how to build proper ER models, so that's why they had to use like free vocabulary and free way to introduce ideas. And with the next steps, they had homework in which they introduced and placed all of these ideas into ER models and then validated against existing role cards, which were a part of the pack of a specific scenario. And the next slide. And actually, we have also submitted the paper for this work to Data Ed Workshop at EDBT, a CDT co-located conference in Finland, and it was already presented there, and the paper is available by the link or by the QR code. That's it.
Thank you very much, Victoria. Maybe you can just reflect a little bit for the students on, how things have gone for you with the program and, what keeps you interested and excited in this work.
Yeah. So basically, since it's like the second year of the program for me, I was super excited about the continuation of the Onion project because we had a lot of ideas how to do it, like the next stages. And thanks to the program, we were able to have few people in the team, so you're not like boiling inside your own ideas, and you have people in the team who you can discuss with, and this was super great. And this was possible to push forward. And the greatest thing for me is that I was able to integrate it in the classes that I teach in the American University Kyiv. So this was super exciting for me. And of course, with the support from my mentors, Julia and George. So we had this feedback loop, so I could actually be able to use it in real world classes.
Yeah, this is really fantastic to hear. Does anybody have any questions for Victoria? We now have just a couple of minutes really of this meeting left, so we can use them if anyone has any questions about the logistics. We can also just talk through the next steps. Does anyone have any general questions? If not, please expect a reminder, I guess, about submitting your project reports from Anya. And we are going to read your reports, talk to your mentors. Please also let us know whether you enjoyed the program, if you would like to continue working with your mentors over the summer. And then we're going to connect with them, look at your report, and get back to you about the next steps. Any questions? Anything to discuss? All good? Well, good luck with the end of the semester, and we'll be in touch. Thanks, everybody, and congrats.
Thank you all for the opportunity.
Thanks.
Thank you. Bye.
Bye-bye.
Thank you, guys.
Bye.
Bye.